ಬಂದ್ ಮಾಡ ಚಂದಾಗ ಊಟ ಮಾಡ ಬಂದ್ ಮಾಡದ್ನ ನೋಡ್ಕೊಂತ ಎಂದು ತಿನ್ಬಾರ್ದ ನೈತಿಗೀರ್ತಿ ಅಂದ್ರ
ಇಲ್ಲ ನಾ ಈಗ ಅಡ್ಮಿಟ್ ಮಾಡಿ
ಅಲ್ಲ ನಿಮ್ಗೆ ಆಪರೇಟ್ ಮಾಡುವಾಗ್ತಲ್ಲ. ಓಕೆ ಅಂದ್ರೆ ಹಾ ಅದ್ ಹೆಂಗ್ ಮಾಡೋದು? ಇನ್ನ ಇದು ಅಡ್ಮಿಟ್ ಕೊಡ್ತಾ ಹೋಗ್ರಿ ಸರ್. ಈಕೆ ಒಟ್ರಿ ಸರ್ ಬರ್ರಿ ಅಲ್ಲ ಸ್ಟಾರ್ಟ್ ಮಾಡ್ತೇವೆ.
ಚಾಲು ಮಾಡಿ ಎಲ್ಲಾ ಫೀಸ್ ಕಟ್ಟಿಸ್
Government school or college has self-cascading results. Shorting fees that
ಗೌರ್ಮೆಂಟ್ ಸ್ಕೂಲ್ಸ್
Participants, please mute yourself. Participants, I will mute you. Our guest will join shortly. Please switch off your audio pods. Please switch off your audio of the mobiles or laptops or computer systems. Mute all ಕೊಡ್ತೇನೆ ಹೇಳ್ತಾರೆ. ಇಲ್ಲ ಕೇಳ್ತಾ ಇದೆ. ಇಲ್ಲ ಮ್ಯೂಟ್ ಆಗಿ. ಸರ್ ಬರ್ರಿ ಇಲ್ಲಿ ಕೂತ್ಕೊಳ್ಳಿ, ನಾ ಸೀದಾ ಇದು ಬಿಟ್ಟು ಕೊಡ್ತೇನೆ. ಇಲ್ಲ ಬರಲ್ಲ, ಇಲ್ಲ ಬರ್ಲಿಲ್ಲ. ಅವಾಗ ಹೆಂಡತಿಗೇನ ಕರ್ಕೊಂಡು
ಅಡ್ಮಿಟ್ ಆಗಿ ಮಾಡಿದವ್ರು ಅಡ್ಮಿಟ್ ಆಗ್ಬೇಕಾಗಿಲ್ಲ. ಅವ್ರು ಲಾಗಿನ್ ಆಗಿದ್ದಾರೆ.
ಇಲ್ಲಿ
ಇದು ಮಾಡಿ ಸರ್. ನಾನು ಮಾಡಿದೆ ಸರ್ ಈಗ.
ಅಲ್ಲ
ಓಕೆ ಸರ್, ಅನ್ಮ್ಯೂಟ್ ಮಾಡಿದ್ರೆ.
Welcome, sir.
Good morning. How are you?
We are very fine, sir.
Okay, I'm here, so we can start as soon as you're
Yes,
ready.
sir. Just a minute. Good morning, all. In
Sorry,
United
your-
States of America, and good afternoon to our Indian friends.
Your voice-
Welcome Dr. Nikhil Gupta to our international webinar. Our principal, Dr. P. K. Bhatt, will just welcome in on behalf of our institute. We are fine, sir.
Good afternoon, everybody. Dr. E.V. Baliga College of Arts and Science, Kumata, a pioneer institute in higher education of Uttara Kannada district, catering the need of students for more than 70 years. Our college is having name as well as fame at national as well as international level. Today, the Department of Physics is organizing a one-day international webinar on physics and materials. So it is my pleasure to invite you all for this particular wonderful seminar at international level, and on behalf of Management College Okay, on behalf of management, on behalf of faculty, I heartily welcome all of you for this particular wonderful seminar. I take this opportunity to welcome Dr. Nikhil Gupta, Tandon School of Engineering, New York, USA. Similarly, I also welcome Dr. Shaijaun, IISCR, Thiruvananthapuram, Kerala. So our physics department is having dynamic staff and students and organizing various events at national as well as international level. Earlier it was a seminar, now it is webinar. So once again, welcome you all and take maximum advantage of this particular seminar. Thank you all.
Now I take this opportunity to introduce our esteemed guest of the first session, the keynote addressee, Dr. Nikhil Gupta from New York University, Tandon School of Engineering. Dr. Gupta actually hails from India, but he has settled in USA. He has been, he is going to be introduced by me for the August gathering. Let me just introduce Dr. Gupta. He is an esteemed professor in the Department of Mechanical and Aerospace Engineering, New York University, Tandon School of Engineering, USA for several years. Initially, he has completed his BE in Mechanical Engineering from National Institute of Technology, University of Rajasthan in 1996. He has got his ME degree from Indian Institute of Science, Bangalore in 1998. He has served as a lecturer at Punjab Engineering College for 1 year in 1998 and 1999. He has completed his PhD in engineering science with a specialized in mechanical engineering in August 2003 from Louisiana State University, Baton Rouge, USA. Then he has joined Tandon School of Engineering at New York University. At present, he is working as a professor of mechanical and aerospace engineering. Dr. Gupta has many feathers in his crown. He has authored 21 book chapters, over 165 journal articles, 75 conference publications, and featured articles in Scientific American, etc. He has also written and edited 4 books, to mention a few: metals, metrics, synthetic foams, carbon nanofiber, reinforced polymer composites, etc. To add a few more feathers in his crown, he has published papers on a survey of cybersecurity of digital manufacturing. His publications include reputed international journals like Journal of Advanced Engineering Materials, Journal of Material Science, and Journal of Materials Today Communications, recently in 2020. Also as a principal investigator on the project for manufacturing advanced tools and devices with Professor Kurt Becker of Applied Physics and Justin Hendricks of the New York Media Lab, Tandon. He is an innovator of lightweight materials honored by Global Engineering Society. He is honored with many awards. To mention few, Brimcombe Medalist Award in 2020, Swiller Medal Award in 2013, Young Professional Development Award in 2013, and Young Leader Professional Development Award in 2007 and 2009. He has a fellowship of American Air Force Summer Faculty administered by American Society of Engineering Education, and Junior Faculty Fellow for Othmer Institute of Interdisciplinary Studies at New York University, Tandon School of Engineering. He also served as a chair of Composite Materials Committee of TMS and membership secretary of American Society for Composite Materials. It is our fortune today to get him as our esteemed keynote speaker of this international webinar on physics and materials. With this brief introduction to the esteemed guest, I am requesting him to deliver his talk to the galaxy of the delegates gathered here online. Thank you, sir. It is over to Dr. Gupta ji. Sir.
Okay, thank you for unmuting me. I was trying to do it, but I was not allowed. Thank you very much for your kind and long introduction here. So let me share my screen. Okay, you have to allow me to share the screen. It is disabled.
Sir?
The screen sharing is disabled. You have to allow me to share
Just
the
a minute.
screen. Yeah.
Sir, will you please see?
Yeah. Okay, sounds good. So, okay, I hope you can see the screen now. All right, so this is a great pleasure for me to speak to physicists because my father was a professor of physics in University of Rajasthan, Jaipur. So I have a special connection with professors and students of physics. I'm myself a material scientist, trained material scientist, bachelor's and master's in material science and PhD in mechanical engineering. So today I'm going to talk about the modeling and simulation approaches for viscoelastic materials. And I'll explain some of these complexities which are very specific to viscoelastic materials. Where I come from is New York University. Now, it's a global university. Actually, it has 3 campuses. The main campus where I'm located is in Brooklyn. And we have other 2 full campuses in Shanghai and Abu Dhabi. So Shanghai and Abu Dhabi campuses offer bachelor's and PhD, not master's degree. And NYU New York campus offers bachelor's, master's, PhD, all degrees in one place. Apart from that, we got 16 total study sites all over the world. That includes Paris, Berlin, London, Madrid, Florence, Washington, DC, and many other places that you can see. So these study sites provides local environment to students who want to be in study abroad programs and take advantage of experts which are available locally in these places. NYU is the largest private university in the US. It has about 58,000 students enrolled and ranked 28th in the country. The university is divided into 17 schools and colleges, which includes engineering, medicine, public health, and everything else that's possible. I mean, Tisch School of Arts is very famous here. Turner School of Engineering is located in Brooklyn. It's very close to Brooklyn Bridge. So if you have seen the pictures of Brooklyn Bridge in many of these Indian movies, I think this first one is Kal Ho Na Ho. I don't know which one is the second one, where you can see the Brooklyn Bridge in the background. So if you've seen these visuals, then in many of these, our building is actually visible in the background in these shots. Lots of Indian students, actually NYU is the #1 destination for Indian students studying foreign in the foreign. And within the School of Engineering, we have almost about 1,200 Indian students. And I serve as the faculty advisor to the Indian Student Association here. So let's get back to the topic of physics-based model and machine learning approaches for viscoelastic materials. If you have any questions, feel free to type in the chat, or I can try to answer the questions if I notice them in the chat as we go along. If I ask any questions, then feel free to type answers to those questions as well and share your opinions. So the work that we have done on this topic, we are thankful to National Science Foundation and the National Academies of Science, Engineering, and Medicine to fund this work. And then we developed a partnership with Anton Par. Anton Par is one of the leading manufacturers of rheology equipment for thermomechanical analysis. So the patent that we obtained on this work, Anton Parr got interested in this work, and then we signed a cooperative working agreement with them. So they provided us with their state-of-the-art equipment for future work, and that the program is called VIP program. And so what this partnership does is it makes our work more relevant to industry and provides a pathway for commercialization of technologies that we are developing. So materials design is a big area. A lot of people are designing new materials for specific applications. Now, everybody wants to design materials for these advanced aircraft and fast cars, but in reality, there are numerous consumer products where material design is important. So some of the challenging areas where they can capture your imagination really is the materials for shoes. And you see advertisement for shoes with lots of different brand names that now this is the new kind of foam, this is the new kind of rubber, this is the new kind of material. And this shoe design is a very dynamic area where a lot of innovation goes in. But then think about the containers that go inside your refrigerator, because these containers are at room temperature. Sometimes you put them outside, and you put them at room temp inside the refrigerator where the temperature can be -4 or -10 degrees C, depending upon the settings. And then we take the same containers out and we heat them up in microwave. The temperature can go up to almost boiling point of water. So the temperature range can be from negative to positive all the way up to about 100 degrees C. So how do you design materials and how do you characterize those materials for properties over that wide range of temperatures? And at the same time, the material has to perform the functions that it's required, and should not change the shape. The chemical composition should be friendly for the food articles and things like that. The other place where I saw, which surprisingly was a toothbrush. So when I was trying to help a toothbrush company select some new materials, I realized that these bristles are designed to become soft under hot water conditions. So if you dip this in hot water, they become very soft. And this is just because the glass transition temperature of this material is low. And that's how the material is selected. So I did not see those kinds of data sheets even for use in cars where modulus is plotted with respect to temperature. Now, the toothbrush was surprisingly an example where modulus versus temperature was one of the charts for material selection. And then there are lots of other products where the requirements for the material performance are extremely complex, like these rovers for Moon or Mars, where temperature in daytime can be 100 or degrees or more, and temperature at nighttime can be -50 degrees. And there is a vast difference in the temperature range during day and nighttime. And the materials still have to perform without much deformation. So how do we select material for these kinds of applications? So here you see that it's not related just to fast cars or advanced aircraft, but the daily routine product that you have in your home. We still need to select materials for them, and they need to perform according to the specifications. Now, the way we have been using the material selection process is this, that suppose we take one of these TPU foams and look at the examples of where this TPU foam is used. So I have a material characterization lab, and we help a lot of companies characterize their materials in our lab. So companies come and they say that, we got a TPU foam composition, and one of our customers is interested in designing a case for a medical equipment. So they would like to know the properties under compression and impact from -10 to 40 degrees C. We want to generate data every 5 degrees C, and the temperature ramp rate should be 1 degree C per minute. Then the other company comes and they says that we're designing this underwater vehicle. The temperature range needs to be -50 to +30 degrees C, and we need to add moisture on top of that. And we need tension and compression properties. Then the another application is shoe, where temperature may be -50 degrees C in icy conditions and +60 degrees C. sometimes in hot weather, outdoor conditions on hot surfaces. And they want this data in minus 10 to the power minus 2 to 1 per second strain rates. Automotive products have a different specification where uh, they want to design these cars for impact at 5 miles per hour to 60 miles per hour. And that leads to minus 2, 10 to the power minus 2 to 10 to the power 3 per second strain rates. And then the temperature range is again minus 50 to 70 degrees C. And then there are these numerous compositions of TPU foams that need to be tested, and properties need to be determined so that people can select the composition that helps in getting the properties they are looking for in the products. So the question that comes here is that this is the same TPU foam that we are testing under numerous different conditions for different applications. And when you take several compositions of TPU foams, the testing just increases by several fold. So how do we deal with this kind of situation where the testing itself is overwhelming? So we wanted to look into this into some more detail. Now, the complication with viscoelastic materials and the definition for viscoelastic material is that uh, when you stretch this material or deform this material, the initial part of the deformation is completely linear elastic, which means when we release the stress, the strain is recovered. But then there is also a time dependent phenomenon. And you can do this exercise with a rubber band at your home. Stretch it for some time, keep it stretched, and then you'd release it. So some part of the deformation will be recovered instantly. And then there will be another component which will be recovered over a period of time. So this time dependent component is called the viscoelasticity. This can be linear viscoelasticity or nonlinear viscoelasticity. So we won't go into those kinds of details just yet, but we want to look into these characterization complexities for these materials because they make it more and more difficult for us to uh, characterize the material properties over all the parameters which are required for these kinds of materials. So here you can see there is this HDPE resin, high density polyethylene resin, very widely used. It's around you in numerous products. And we are testing this material at extremely slow strain rates like 10 to the power minus 5. And here the highest one is 10 to the power minus 2. So all these are quasi-static strain rates allowed by ASTM standards. But you can see that within this very slow strain rates, there is still remarkable strain rate sensitivity in this material. The black line here is 10 to the power minus 5, and this magenta line here is 10 to the power minus 2. And they are far apart. You can look at the numbers that at the strain of about 0.005, we are here at about 3 and here about 7. So in these cases, the values are quite different. There are other materials that have strain rate sensitivity in a very different range of strain rates. And this is where you can see that magnesium alloys 800 per second to about 1200 per second strain rates. So compared to 10 to the power minus 5, this is about 7 or 8 orders of magnitude higher strain rates, but it does show strain rate sensitivity within this range. So we have to figure out test methods that can work and provide us the data over these parameters. So if I plot the elastic modulus for HDPE with respect to temperature and strain rate, then there will be a plot like this. It's a three-dimensional plot based on these three parameters. So imagine how many tensile tests needs to be conducted in order to calculate modulus to plot a graph like this. So now we have 10 to the power minus 5 to 100. That means 7 orders of magnitude in strain rates. And the temperature is varying over about 85 degrees in this case here. So if you are conducting these tests every 5 degrees C, as one of the applications had mentioned, so we are looking at maybe 15 different temperatures and 7 different strain rates. So it's about 105 different conditions at which we would be generating data. And you know that every tensile test needs to be replicated 5 times. So that means we are looking at about 525 specimens to test before we can plot a graph like this. And that's a lot of tensile testing. And for companies, it's not just that the number of tests is the problem, but the amount of material needed to conduct that test is a lot of material. So if you are a company developing material and initially you are testing novel materials which are quite expensive to produce, and then you have to conduct 500 or 600 different tensile tests. It's a lot of material to produce, conduct the test, and that expense itself becomes overwhelming in material development exercise. And it's not just that, but 600 tensile tests, some of which are at very, very slow strain rate, like 10 to the power minus 5. So this slow strain rate test will take forever to complete. It will take like at least about 6 to 8 hours for these kinds of materials before you can get the reliable data out. So that's a lot of machine time that is required to get this data. So the question here is this, then can we come up with something to make our life easier and plot this graph with fewer tests without the loss of accuracy? Okay. Now, the other problem here is this, that not a single equipment can test all the materials from 10 to the power minus 5 to 10 to the power 4 or 5 that we are looking for. We have a range of equipment that we use for different purposes. So universal testing machine, the one like here, the Instron machine, it can test usually from 10 to the power minus 5 to 1 per second. The hydraulic machines can go up to about 100 per second strain rates if you're lucky. Usually they go up to about 10 per second. Then the split Hopkinson pressure bar, this equipment became commercially available only recently. Previously it was built by people who wanted to use them. So our equipment is home built, and this machine can go up to about 500 to about 5,000 per second strain rates. Then there are many other methods like Taylor impact. It can go up to about 10 to the power 7. Explosives go 10 to the power 7 to 10 to the power 9 per second strain rates. So there is no single test method that goes across the entire range of strain rates to provide us with the data, which also means that you need to invest in multiple equipment if you want that data over a wide range of strain rates. Apart from that, there are other methods like DMA, dynamic mechanical analyzer. This equipment is based on the vibration response. Then there are free and force vibration testing methods, then ultrasonic imaging methods, all of which can provide you some measure of modulus, if not the direct modulus, and they can be used. Now, think of also the complication that you need the data at high temperature. So you need furnaces mounted on these methods. And high temperature Hopkinson bar testing is really a very, very difficult area where you need to apply compensation factors for the bars which are used to obtain the data. And those fields are never easier to deal with. So here is the question for you that you need to think about. It's a very fundamental question. Suppose magically all these equipment had the capability of conducting the experiment from 10 to the power minus 5 to 10 to the power plus 5 per second strain rates. The modulus measured from each equipment, would that be the same or different? Would it be comparable to each other or not? And this question you can think a little bit deeply. If the chat is allowed, you can answer, you can type your answer there. So the question again, I'll repeat, is this, that if these equipment all somehow had a capability of conducting the test from 10 to the power minus 5 to 10 to the power plus 5 per second, would the modulus measured from these equipment on a material would be exactly the same quantity or different? So when we look deeply into this question, it turns out that the operating procedure or operating principle of each of these materials, each of these equipment is very different. It's built on different sets of equations. And it is very difficult to claim that they are going to measure exactly the same quantity. So then exactly what is the modulus? That question came up. Now modulus is, the definition itself is very simple, that you apply a stress and measure the resulting strain, and the slope of stress versus strain diagram is modulus. But where does this modulus really come from? So since you are all students of physics, you know about the interaction between atoms, you know about the interatomic forces. So modulus is nothing but it's the force that is required to increase the interatomic distance without displacing the atoms from their location. So that is the kind of force that we are studying here when we measure the modulus. Of course, there are lots of complications for different types of materials, like in polymers, especially long chain, linear chain polymers. The secondary interactions may become more important. Sometimes coiling of chains becomes important. When you apply the force, the uncoiling starts to take place, and that becomes something that you need to measure. So keeping all that in mind, we'll just go to the basic definition and say that this is something that we can always recover. And that's what we are looking for in our modulus. Okay. We looked into this problem a little bit more deeply. And, and here you can see that we plotted these graphs for two different types of foams, and we have plotted these graphs for many other different types of material system. So in case of polyvinyl chloride foam, PVC, and the aluminum foam, we extracted the data from a number of published studies. This is not our data. Some of this may be, but mostly it's taken from other studies. Then what you see here is that despite having all these different types of methods, there are still large ranges of strain rates where there is no data available in the published literature. So usually for PVC foam, you can see that from about 1 to about 500 per second strain rates, there's no data reported in any of the studies. For aluminum syntactic, for aluminum foams, same range, about zero 0.1 to about 500 per second. There's no data reported in any of the studies. So if the tests were that simple, and if you have so many different machines available, why is this discrepancy that there is this range where there's no data available? Because if the machine could go, people would have reported data. These are very common materials out there. So that became a question in our mind, and it turns out that this is a fair observation that the hydraulic machines don't go to about 100 or 500 per second, whereas Hopkinson bar is not able to come down to about 100 per second. And there is this range which is not covered by any of these equipment. So these are multiple questions that I have posed so far, and we need an answer to these questions based on the basic physics that governs the materials and their properties. So here what we did was we looked into these equipment one by one, and conducting these tensile tests is very difficult or challenging problem. You need a lot of material, and if you have to mount furnace to conduct this testing, it just takes too long to conduct all the tensile testing. So we selected this equipment called Dynamic Mechanical Analyzer. It's called DMA. And the way this equipment works is that you can have different configurations here for material gripping. So in this case, there are two clamps, and a beam-like specimen is clamped between them. At the middle part, we can apply a load to bend it. So this is called dual cantilever configuration. And then this applied load can be at a different frequencies. So for viscoelastic materials, if you keep loading this material up and down at certain frequency, a lag will be developed between the stress and the strain cycle. And once this stabilizes, then you can measure the phase difference between them. The energy stored in the material in one cycle gives you the measure for storage modulus, and the energy dissipated in one cycle gives the measure of loss modulus. The ratio of loss to storage modulus is called tan delta, or the loss tangent. which is a parameter used for damping capability of materials. These experiments can be run in different configurations. So if you are measuring storage modulus, it's called E prime. If you are measuring shear modulus, it's called G prime. But the nature of these curves remains about the same. That storage modulus is this solid line, thin solid line, and the loss modulus is this dotted line. So this is also the best method to measure the glass transition temperature. It is better than DSC to measure glass transition temperature because you can see these sharp peaks in loss modulus. The temperature of this sharp peak is actually the glass transition temperature. So, and then there are these different temperatures of alpha and beta gamma transitions, which can be measured from the same experiment. Now, when we are conducting these experiments in different temperature ranges, like for this particular material, if you're conducting the experiment from room temperature, which is about 30 degrees C to high temperature, you will capture only one peak, which is glass transition temperature. But if these experiments were conducted from minus 150 to about 250 degrees C, then you'll capture these additional peaks for thermal transitions in the material system. So what you see in these graphs is dependent upon the temperature range that you are looking for. But the storage modulus is always this line that storage modulus decreases as you increase the temperature, which is also the trend for elastic modulus or Young's modulus. And I'll go into the difference between the two terms very soon. So how do we deal with these viscoelastic materials? Here is this basic equation. Let me see if I can get a different, yeah. So E prime here, it's called storage modulus, and E double prime here is called loss modulus. They are related to each other by this complex function. And E star is called a complex modulus. Now this complex modulus is not elastic modulus, it's not Young's modulus. This complex modulus is E prime plus iota E double prime. So storage modulus plus this complex function and then loss modulus. E star is a frequency dependent quantity, whereas Young's modulus is a time dependent quantity, strain rate dependent quantity. So that's how they are different. Now, if you have a response like this, and if you have had some training in viscoelasticity, what we have been doing for a long time is we measure equations like this, calculate the E star or take the E prime. And then we say that suppose this is my graph for E prime with respect to frequency and temperature. What we can do is take the graph at the room temperature. So suppose this one is the line at room temperature. I'm just picking up arbitrarily for now. And the graph. What you can do is you can plot this to zero frequency theoretically, and then extrapolate this line to zero frequency and calculate the value for modulus at that point, and then just call it elastic modulus or Young's modulus at zero frequency. So this is what we have been doing for quite some time in this case. Let me just find out the way I can delete what I wrote down. Sorry about that. Okay, sorry about that. Yeah. So if we extrapolate it to frequency 0, it is supposed to give us a measure for Young's modulus. But we are doing a lot of things here which are not in our favor. So first one, most people would do this testing at 1 hertz of nominal frequency. And that's what most of the data in this field is in the reported literature. What you can also do is run this frequency sweep, and you can get this complete frequency versus temperature data. If we extrapolate it to zero frequency, effectively what we are doing is neglecting the frequency component completely and making this graph actually useless after all the testing that we have done. Now you can also look at these this graph on the right hand side here. What this graph shows us is that even at very low strain rates, there is remarkable strain rate sensitivity in this material. And all these strain rates are allowable by the ASTM standards. So extrapolating it to the zero frequency is really not the best idea, because you don't know which strain rate you are going to end up with in your actual tensile test. And extrapolation to zero frequency means zero strain rate, which means 10 to the power minus 9 or 10 per second strain rate. But here you can see that actually there is remarkable strain rate sensitivity in this case, and the data that you will get by extrapolation will not be equivalent to what you are measuring from your tensile test. So tensile test is at certain strain rate, and that's what we have to capture in our tests, even when we extrapolate from the DMA data. So the question comes that, first of all, what exactly is this E prime? How is it related to the elastic modulus? And how do we find out the way to recover the elastic modulus with respect to temperature and strain rate from the data that we have for the storage modulus? So these are some of these questions that we are trying to answer here, and see what comes out of this exercise. So what we did was we looked at the definitions again, and then it turns out that we can conduct this time temperature superposition to develop a master curve. So now, if you have conducted any testing, and this is from the general experience also, that when you heat up the material, they become softer, which means their elastic modulus reduces. And when you increase the strain rate, the elastic modulus increases. So decrease in temperature is technically similar to increase in strain rate as far as the modulus trend is concerned. So now when we conduct the time temperature superposition, these are the kind of trends that we are going to capture in our work. So what really happens is that we pick any of these temperature as the pivot temperature. Let's say that you picked 85 degrees C as your pivot temperature. So all the graphs above 85 will shift to right, and all the graphs below 85 will shift to left. And you keep shifting there until you can find one single graph, a continuous graph, and this graph is called the master curve. So I see a chat message here that just various forms will textile materials like glass fiber, geogrids also fall in viscoelastic as they are ASTM creep test applicable. Yeah, so this is correct, that a lot of these materials, and I'm going to show you results for composite materials at the end once we finish the model. So this master curve can be created here, and there is a term called rheologically simple material, which means if you can develop a master curve for a material, then the material fits on the definition of rheologically simple materials. Now, once we fit this master curve, it's at a given pivot temperature, but then you are shifting the curves on the right and the left, which means at the frequency, you are stretching the frequency scale. And what the master curves give us is the data from 10 to the power minus 10 to about, actually it goes much wider, it goes to about 10 to the power 6. But we are cutting it off here because data is not reliable after these ranges here. 10 to the power minus 10 is already extremely slow, and 10 to the power 4 is where we need to capture additional transition temperatures. So that's why this range is selected here. So once we select these curves, then we can fit an equation on top of it to estimate this. And this equation will be useful for us. We call it a master curve. The equation for this master curve is selected based on certain requirements. Now you can see here that it's going to go asymptotic at lower frequencies, and it's also going to go asymptotic at higher frequencies unless there is something abnormal going on there. But that's what the trend that you see in the range which is visible. And also there is a change in slope from low frequencies to high frequencies. So that's how we need to select this equation for master curve with all these properties. Then we can integrate this curve and with respect to frequency and temperature, and we can get the values out from there. So ET is called the relaxation modulus or relaxation function. That's what we can capture from this master curve. And once you got this curve ET, in that case, we can apply this stageless convolution, which is E is the elastic modulus, and the second term here is the strain rate. Once you integrate this equation with respect to temperature, that's when you can capture the value for stress. And this equation can now be used to calculate the value for E. So based on the equation that we had selected here for the relaxation function and the integral that we get here, this integration is conducted partially numerically because the equation is a convolution and it's not possible to get the direct integration of that easily. So this numerical way provided us with a method to capture the integration more easily. So that exercise we can do for various pivot temperatures, and eventually we can get the elastic modulus out at various strain rates and temperature. So this exercise gave us the elastic modulus, and in this case, we captured the secant modulus because there's no straight line portion in the stress strain graph. Now this data is at strain rates and temperatures. So going further, what you can look at is what we were capturing is a graph like this from our work, that elastic modulus with respect to temperature and strain rates is what we got out from our calculation. Yeah, so I think somebody is trying to answer, trying to ask a question, but question is not written yet. Some of these values we extracted and then we did the tensile test. And in this case, we obtained the data from published studies, and we tried to use the existing data to validate our model, and the extracted data fits very well. So what you can imagine what we have achieved here is very simple. The entire chart of elastic modulus with respect to temperature and strain rate is captured from just one single experiment in DMA. So we did the temperature and frequency sweep on that one specimen. And once we applied our scheme of conversion, then this entire chart of E prime or the storage modulus is now converted to Young's modulus with respect to temperature and strain rate. So you can imagine that we had required 600 plus specimens to capture the same kind of data from tensile tests, but now we don't have to do those 650 tensile tests, but we get the data from one sample. It takes about 8 hours, and we get the same kind of data set from there. So this kind of transform was validated on PVC, polyvinyl chloride, polycarbonate, epoxy, vinyl ester, and many types of micro and nano composites, fiber reinforced composites. There are some special conditions for directional materials like fiber reinforced composites, but other materials like just the plastics, PVC, polycarbonate, epoxy, and vinyl ester, this was pretty straightforward. So the other important thing here is to understand that we didn't do any hardware modification, that there was no modification to the test method. Same DMA experiment, standard test specimen, 10 millimeter by 55 millimeter by 5 millimeter. That's the dimension of the specimen. A lot of this data you already have, but now we have a new step of converting the data from storage modulus to elastic modulus and just extract this more information out from there. So I think the question somebody asks is TPU foam safe for babies or old people? But that's not the question I'm trying to answer here. The only question I'm trying to answer here is that how do we get the properties out from any viscoelastic material, and TPU foam is an example, with very little effort instead of doing numerous tensile tests over months of time requiring a lot of material. So the material requirement is reduced, the testing time is reduced to about 8 hours to conduct this kind of experiment. And we get the same amount of data. So that's what is important for the industry. So we can also do the same kind of testing from storage modulus. If you got the storage modulus, in that case, what we would do is just apply this Kramer-Kronig relationship to convert it into loss modulus, because as you saw, the equation was very simple. For complex modulus, it was E prime plus I E double prime. So E prime and E double prime are related to each other. When we are playing with the storage model loss modulus, what we can do is we can apply another method where we can first estimate a frequency dependent and frequency independent component of modulus. The frequency independent component can just stay like that, and the frequency dependent component can be converted into the time dependent information, and then we can add it up back to recover the elastic modulus. So equations are simple here. You can see instead of sine, we got the cosine at this time. If you are starting with the loss modulus, and then you can go back to the same scheme of equations and find the elastic modulus. So this Kramer-Kronig relationship is important in this case because it defines the direct relation between storage and loss modulus quantities. So the data again is validated with a number of different polymers. Here you can see vinyl ester and polycarbonate data coming from DMAs in these lines, and we obtain data from some of our tensile tests and also tensile tests which are reported in the literature from other groups. And these could be at any strain rates, as you can see, within the same 10 to the power minus 6 to about 1 per second strain rate. And this matches pretty well. So the effort is reduced quite a bit, and that's important for viscoelastic materials. Now, the next question comes that this graph that we are obtaining, it is still taking us about 8 hours to generate on a DMA. So the way DMA does operate is we run this load cycle until it reaches an equilibrium. After that, we ramp up temperature. There is a ramp rate, and then the next temperature is defined about 5 degrees higher. And then we do the testing again. So let me just go back to the previous chart one more time for quick reference here. So we'll just stay here. So here you can see that 40 degree, 45 degree, 50 degree, 55 degree, and the testing is going on from 40 degree all the way to about 120 degrees. So these lines are at numerous different temperatures. At every temperature, we are taking a number of frequencies. So we take 1 to 100 hertz, but usually we divide it into 2 parts, 20 parts at log axis. So 20 different frequencies, and at 5 degree intervals, these are numerous temperatures. So actually, when you look at the graph like this, we have 560 points here within this graph to get this entire data point. Now, the question that came up is that, do these 560 data points need to be taken, or can we further reduce this testing regime and still get the same accuracy of data? So from months of tensile testing, we are down to 8 hours, but we're not satisfied yet. So what we realized here is that the storage modulus graph or the Young's modulus graph always comes with the same kind of profile. So it's starting in the left here, and then it's continuously reducing. The slope is changing, but the trend is just reducing as you increase the temperature. We can use this kind of information and try to model this entire surface as in one step rather than taking those 560 points upfront. So here what we did was we started with a particle swarm algorithm, and these methods are well developed in the literature for how to estimate the surfaces. I'm sure you might have studied the topic in one of the math courses. So the way particle swarm algorithm works is that you take a set of points and randomly fit those points on this surface and then see if you can capture the qualities of the surface properly or not. If you don't, then you increase the number of points and then you keep doing it until you can capture this surface properly. And at every step, you can run some tests. So you can start with maybe 3 points to start with, and then you keep adding points until you are able to capture this surface with a good quality of fit here. So in this case, the particle swarm algorithm, which is the simplest one, what you can see here is that about 100 points give you pretty good convergence. The error is below 0.1% in that case. If you are happy with the error of say 0.5%, then we are looking at only about, let's say, 15 or 20 points here where you can get good convergence. So that's an important number. So instead of doing this standard scheme of 560 points for measurement, what we can do is superimpose this particle swarm algorithm. And based on the accuracy that we want in this data, we can do this optimization and find out the value for based on like 20 points to about 100 points. So that reduces the testing time further. And many of these sampling methods are now available. There's Monte Carlo, Latin Hypercube, Halton quasi Monte Carlo, or Sobol quasi Monte Carlo method. So these are more advanced methods than particle swarm algorithm. But then here the trend that you see, that average error reduces less than 10% in most cases with as little as about 10 points. The Sobol is quite powerful method in this case. With less than about 10 points, you can capture the data pretty nicely. And what it does is that only 10 combination of temperatures and frequencies, if you have to measure, in that case, the testing would take less than half an hour of machine time. And then you have the entire chart with about the same accuracy as you used to have from tensile test. So what we were able to achieve in this case is the months of testing was first reduced to 8 hours, and then we further reduced it to about half an hour, and that was quite useful. If you can do this with loss modulus, I demonstrated that you can also do this with storage modulus because they are related to each other by Kramer-Kronig relationship. But then loss modulus is nothing but it's related to loss compliance, and loss compliance is related to storage compliance. So no matter which data you have, you can always run the same calculation, and then you can achieve the modulus of the material. And DMA is just not related to the standard equipment DMA, but it's the cyclic testing scheme. So technically, any cyclic testing like fatigue testing also is quite similar to what we have been doing. We haven't expanded the work to fatigue yet, but I don't see a reason why it would not satisfy those conditions. And here the data actually is coming from nano indentation. This nano indentation is used a lot these days for nanocomposites, nanomaterials, or biomaterials. So I just picked the example for biomaterials working with one of the groups in medical school here. So they did this kind of testing on larynx, which is the vocal fold tissue here. And they tried to create the storage modulus maps from the nano indentation testing. So we took their data and we did nothing else on their hardware scheme. It's the existing data that they had, but we applied our method. And eventually we came up with the storage modulus to elastic modulus conversion here. So the way this nano DMA works is that there are two methods. One is the Oliver Farr method for nano indentation. In this, we increase the load, and then we hold the load at some point. Finally, the load is released, and from this relaxation, we measure the slope of the relaxation part to calculate the modulus. From the Oliver Farr method, the more evolved method is the CSM method. It's called continuous stiffness method, in which the load is constantly oscillated. And based on this frequency, you can measure the elastic modulus under different conditions. So the CSM data is what we are using here for conversion to elastic modulus. So once you are able to convert the storage modulus to elastic modulus, here you can see that the fitting on the data with our model is quite close compared to what has been measured from storage modulus here. So the method can be useful for a wide range of accuracies. Now, the question here is also that can we apply this artificial neural network to estimate the properties of materials? And why do we want to do it? There are several reasons for doing it. Now, first of all, the artificial neural network architecture is very similar to time temperature superposition principle. It's not the same, but the architecture is similar, and we can take advantage of that. The second point here is there's a lot of data generated in DMA. Not a lot of mechanical test methods generate that amount of data. So DMA provides us with a possibility of actually applying this artificial neural networks, train the neural network properly, and then use it for certain predictions. Many times people would ask question that uh, the artificial neural network methods are only used for interpolation. So what is the benefit of doing that for interpolation? So the benefit actually is not in solving the forward problem, but it is to solve the inverse problem. Because if your customer comes and they say that I would like to have a material with certain elastic properties, what should be the material composition? A lot of times solving these inverse problems don't have a unique solution. So you would like to conduct the multi-criteria optimization, you would like to get into more specifics of it, and then the modeling scheme becomes more and more complicated as you apply more and more parameters there for multi-criteria optimization. And for problems like this, then the neural network or machine learning methods become much more friendly here. So the architecture here that we are going to use is going to be very standard. We are not inventing new machine learning methods right now. We are not inventing new artificial neural networks, but these are standard methods, and we are going to see how well they apply to our kinds of problems. So if you're starting with storage modulus, it's a little bit straightforward. If you're starting with loss modulus, then you would have to have an extra hidden layer for Kramer-Kronig relationship. And the benefit here is that if you have both data storage and loss modulus, you can use KK relationship at some point in this architecture to cross-validate the data and make sure that it matches up, that there is no discrepancy there. So in our case, we divide the data set into training, validation, and testing set with 65%, 15, and 20%. And once this is trained and validated, in that case, what you can do is you can just use the same architecture and use it on different compositions, and then try to find the values for different material compositions and estimate the elastic modulus for there. So I won't go into the architecture of these neural networks, but here we use the L2 regularization or the ridge regression method and train this neural network. We use both storage and loss modulus component, and in between in this layer, try to use the KK relationship to cross-validate the values which are coming out from there. So Pearson's correlation coefficient, this predicted storage modulus versus experimental storage modulus from the trained data set. The R value is 0.999, which is pretty good. And then we can calculate the heat map for the error. And this error map shows that there are some pockets where error is a little bit higher, but more or less it's within, I think, 3% for most part of this graph. So that's pretty good for materials characterization field. And then we tested this for graphene epoxy composites and EVA, apart from many other different polymers that I had shown before. So nano composites at the macro scale, you can take them as the homogeneous materials
And the data matches extremely well for materials like that predicted from the neural networks. So this work was featured on the inside cover of the Advanced Theory and Simulations. We conducted the experiments on fiber reinforced composites. Architecture again remains the same, but the directionality of fibers becomes one of the considerations here. So one of the layers was related to the storage modulus at 0 degree, 45 or 90 degree, which means different directions of fibers. With these different directions of fibers, you have to take the stiffness matrices differently. So we calculate those stiffness matrices for different directions. And using those stiffness matrices, we come to storage modulus in any direction. And finally, on that, we apply our transformation to calculate the elastic modulus. And the data again matches pretty well, as you can see from these validation graphs. And this was published in Journal of Composite Materials recently. And finally is the case of materials design, where we solve the inverse problem. That starting with the properties that we are looking for, eventually we go into the material composition. So we estimate the storage modulus that would be needed to provide the right set of properties in the final material. And then we select the material based on that. So a number of different materials here, different volume fractions of particles in this material. This is a particulate composite, syntactic foam. And you can see the data matches pretty well with our predictions, more or less. The predictions start to deviate when you go to higher strains, simply because the viscoelasticity at those strains actually changes to nonlinear viscoelasticity, for which these equations are not yet designed. But that would be the next thing to do in our case. So these are the materials characterization charts that we have developed based on the scheme like that. So in conclusion, what we were trying to do was develop this scheme where viscoelastic properties are converted to elastic properties. So storage modulus is measured very often, but storage modulus is not something that we use as any modeling or simulation. We don't use this quantity in finite element analysis. What we need really is the Young's modulus. But having the frequency dependent quantity like storage modulus was not very helpful in that case. So we developed this transform where viscoelastic properties were converted into elastic properties, or the Young's modulus, and the frequency component was converted into the strain rate. And that was very useful, that in a single step, we could get the Young's modulus with respect to temperature and strain rate. So that reduced the required 560 points required 650 tensile tests to just 1 day of DMA testing, which was about 560 points within that data set. And then we conducted the data reduction, where those 560 points were further reduced to about 40 points with good accuracy in the system. So the effort was reduced to about half an hour of total testing time. And this artificial neural network approach provided us with further flexibility for optimizing the material composition. And we were also able to solve the material design problem based on that. So thank you very much. That's all I had on my side to present, and I'll be happy to take any questions here.
Thank you, sir. Now the session is open for the questions to Dr. Gupta. Participants can ask questions. He will give you the particular things like answers, whatever you want in your own fields, etc. Like.
Yeah, so one thing I might want to mention that, there are certain limitations to the transform I showed. And one limitation I'll mention is this, that we can capture one change or one glass transition temperature in our scheme. But as I showed initially that some materials may have alpha and beta transition temperatures also. And in those cases, you would have to conduct this calculation piecewise and then combine it all together. If you want to model all of it in the same equation, then the nature of that equation becomes more and more complicated. So here we are solving it for 4 unknown constants in our equation. If you had 4 glass transition temperatures or 4 thermal transitions, then you would have 16 different constants to solve for. And writing an equation with 16 unknown coefficients and solving it, you require a set of 16 equations, and that becomes an overwhelming exercise. So we have to find additional methods now for more complex material systems.
Any more questions, please? Please type in the chat box. Sir will answer within next 15 minutes to your questions. Any research scholars in this field, you can ask the questions. Any students from any college, any university, you are welcome to ask the questions to the resource person, Dr. Nikhil Gupta.
Yeah. Has anybody used DMA in their work yet? Or has anybody conducted high temperature tensile testing ever? You can write in the chat box or unmute yourself.
Sir, just a minute. My colleague will ask one question. Dr. Pai, he is going to ask a question. Please.
Sure.
I mentioned about ANN, artificial neural network.
Yeah.
The question was whether you have used Keras or TensorFlow or such kind of thing, or you built yourself.
Yeah. No, we use TensorFlow for most of the work because, my strong belief is that at this point, when we are starting to apply this neural network to material science field, where we are not the experts of building neural networks or building new approaches yet. So how the existing resources can be useful for us. So it took me only 3 days to train a student to use the TensorFlow, and the student was able to produce excellent results after that. And now one student is training the next student in the group on the TensorFlow. So it's very easy, I think. It's pretty easy to apply to many of these material science problems. But the question here is really to have the high quality data that can train the neural network without the bias, and you are able to ask the right questions from this neural network for optimization.
And
Okay.
one more thing here. You are using some, let me reframe it.
Yeah.
So you have mentioned that 15 to 16 parameters.
Mhm.
So how many hidden layers and how many layers we may need to train them?
Yeah. So it depends upon the material composition also. And in this case, I didn't show you some of the graphs, but our papers have all these kinds of tests. So we have only temperature and frequency as 2 of the parameters. So in that case, we could get by when we do the optimization, we only needed 2 neurons and 2 hidden layers in order to get the optimized values. But if you add more parameters upfront, like in case of fiber reinforced composites, the volume fraction of fibers and the orientation of fibers for additional parameters, in addition to temperature and frequency, then we needed 4 neurons and at least 3 hidden layers in order to solve those kinds of problems. So it doesn't depend upon the number of thermal transitions as such, but it really depends upon the number of independent parameters or seemingly independent parameters that you are trying to use in your data set. Okay, but it's a standard procedure. I think the question is very important for people who have not used neural networks yet. So look at the TensorFlow, see how the architecture actually works. And
Sir, may I ask you
Yeah.
one small question, which is just coming in my mind?
Yes.
Any new kind of advanced viscoelastic materials you are using in aerospace technology for the recent one, what you have just can just update.
Can you repeat that question, please?
Any advanced viscoelastic material which is needed in your aerospace applications like that or not?
Yeah. No, so the question that we are trying to solve here is really the viscoelastic material characterization. So if you are using a different material, if you are inventing a new material, usually you would have a number of different chemical formulations. And then you would have to test all of those formulations to find out what their properties are. And then select one for your aerospace application. But instead of testing 10 different materials with 600 different tensile tests each, you are looking at 6,000 tensile tests. We want to reduce that to just 1 day of DMA effort. That's how we are trying to do it. So it doesn't matter if your material is very standard, which is what we have used. I've shown results because tensile test data from other groups are available on those existing materials. But once the method is there, now you can use it for your novel material. So here I'm not showing you results on novel materials as such. Okay. There are a couple of other questions in the chat. I think somebody said, Rohit is asking question. Various Monte Carlo methods were mentioned. Can you elaborate about limitations and direct implications towards interpolation of data in order to reduce test set? Excellent question, Rohit. So here you see this heat map. Oh, sorry, let me go back. You asked about the interpolation methods actually. The comparison is right here, and it depends upon the type of data that you have and the nature of the data. So if you were applying just the Monte Carlo method, a standard Monte Carlo method, you need about 25 data points before you can get to the average error of about 10%. This average error is a little bit of a misnomer simply because there are a couple of points which are very high in error, and there are most of the graph has much lower error than most of it. So with 25 points, if you were taken same 14 points here as 3 other methods for Monte Carlo, your error is going to be much higher in that case. So we have to be careful about the nature of our data set and select the right method accordingly in order to get the high quality results. Half an hour is a little bit too little, so I would say that you can increase it to about maybe 25 to 30 points. And then all of these methods are going to provide you with much better results in that case. So any method that you select, it has to be according to the nature of your data set. And fortunately, one thing that I can point out that the storage modulus plot is always this waterfall plot where the slope is always reducing at different rates. And we are able to capture that using these methods here. Vibha asked a question that why can't finite element analysis is used for finding the properties for material instead of using machine learning. So finite element analysis is mostly it uses the input of material properties to calculate the deformation behavior or the deformed shape of the material system. So modulus is a very basic input parameter for much of the finite element analysis that we do. You can try to solve inverse problems, but that's not really very standard. It's a very time consuming and very little benefit out from that kind of problem. So that is the reason that we need the elastic modulus upfront, very reliable values before we can go into using FEA for the design problems. What is the function of normal probability plot in analyzing the results of DOE? So in a lot of these cases, normal distribution is taken, but here we don't care about the distribution or DOE in this case. What we are doing is it's just the experimental data in its native form that is obtained. And I don't care what is the probability plot or distribution or DOE in this case. DOE part is only related to somewhat here, but again here, depending upon the data set, I still have to develop my own method before I can reduce the test scheme. So think of this problem as much more complicated. That suppose you have a very reliable data set coming from tensile tests. Would you like to create a DOE method that gives you 10% difference in the data set? So I would say that it depends upon application, that if you are designing a child's toy versus designing an aircraft, you may have different probability plots acceptable or different DOE schemes acceptable for both of those kinds of applications. So I'm leaving that possibility open for you to decide what you would like to do at the end of it. Any other questions here? So thank you very much. I think the questions are not there anymore, but if you still have some questions, feel free to ask now or in the chat. So this method was patented by us in the US. We already got the patent last year. And now with the partnership of Anton Par, we are hoping that this will make into the mainstream equipment where you might have an additional step of data processing, or you might have this quick test mode where in half an hour you'll get the entire data set, where accuracy may not be as great as you would have in the full set, but again, it gives you an indication where you can quickly know if your materials development is going in the right direction or not. Okay, there are no more questions, I think.
Participants, please, if you have any question, please type or ask to the resource person as immediately as possible. There is still time because the second resource person has not joined it due to his some urgent personal work, but he will join shortly, so that Dr. Gupta is waiting for you all, the participants, to be answered for your questions. Please ask. So, thank you very much, sir, for giving this valuable keynote address to our students, researchers, and all the faculty members all around the India and in other parts of the world. Thank you very much for your kind cooperation to organize this seminar. I once again thank you, your own participants, your students, and those who also joined this seminar. Thank you very much, sir. If you are waiting, you are again welcome because Shahidmoon will join shortly, sir. Please be on. So here is a small announcement. Dr. Shahijmoon will join within next 10 to 12 minutes. I'm very much thankful to Dr. Gupta. He's waiting for a second resource person to see. Okay, sir, I'm very happy as you have rejoined. Thank you.